Let's learn a very important skill, and that skill would be to graph a rational function. I'm Mr. Ish and I'm welcoming you to this video. We're looking here at the graphing of two distinct types of rational functions. We have one of this form and we have that form. What is it that I'm trying to demonstrate here by means of this representation? When you're looking at this, you're looking at some sort of rational function, which is some number here on the top, and this is just an example. It would be like 5 divided by a polynomial expression in the denominator, something like 5 minus x or whatever. But here we're looking at such an instance where the denominator polynomial has a exponent of 1, the numerator polynomial has an exponent of 0. You can see that clearly. In this particular format over here, we're looking at a polynomial expression in the numerator and 1 in the denominator. We're looking at a representation such as like 3 plus x over x minus 7. You see over here you have an exponent here of 1, exponent here of 1. Those are the two distinct forms that you want to look at. And let us start here with this particular form, and we will show you how you can graph these, because your ability to graph a rational function will help you very much when you're doing limit questions in calculus. We'll show you one example of this, one example of this. Let my first example be here, example A, and it is represented by this 3 divided by x minus 5. You have to graph this. When you're looking at this, you know there's no real exponent here in the numerator, but there is some here in the denominator. When you have a variable with an exponent in the denominator but not in the numerator, you're looking at a certain type of a horizontal asymptote which will generate. But the steps are these. Understand what it is you have in terms of either this form or this form. These are not the only forms, but these are the main forms. Start here with the determination of a vertical asymptote. You look here at the 0 of your denominator, and we can just say 0 of the denominator. X minus 5 equals 0, x is equal to 5. This here is your vertical asymptote. Step number B, determine a horizontal asymptote. When you have something like this, as I was alluding to maybe a minute ago, when you have something here in the numerator to the power of 0 in terms of an exponent, here to the power of 1, the denominator exponent is higher than the numerator exponent, then you have a standard horizontal asymptote. And what is that? That's your x-axis, or y equals 0. You've already determined two of the most important things you need to graph this rational function. You have a vertical asymptote, x is equal to 5. You have a horizontal asymptote, y equals 0, which is your x-axis. You have a rough representation here. Now you have to determine your curve. And the best way to do your curve determination is this. You plug in a value of 0 in places of x. I'm just cleaning this out, and see what happens in terms of y. When I put the 0 here in places of x, I'm doing really a f of 0. That's what I'm calculating, f of 0. I put 3 divided by 0 minus 5. I get a 3 over minus 5. And that tells you you have a y-intercept. 0 comma minus 3 over 5. This is what it looks like. It clues me in as to I'll have some curve here in this quadrant right here, and I'll have some curve here in this quadrant. Now what I can do is come out with two arbitrary points to the right and to the left of the vertical asymptote. To the right of the vertical asymptote, I can think of a value 10. To the left of the vertical asymptote, I can think of a value, let's just say minus 10. When I put here value of 10 here, I'm getting a 3 divided by 10 minus 5. I'm getting a 3 over 5. When I'm putting minus 10 here in this function, I have 3 divided by minus 15, which is 3 divided by minus 15, which is minus 1 over 5. These will help you do your curve. At 10, I have a value 3 over 5, which is not very large, so that's telling me I have a curve which is looking like this. At minus 10 comma minus 1 over 5, I have a value which is close to your x-axis, because it's going to approach the horizontal asymptote. I'm looking at a curve which is looking something like this, and now my rational function is graphed. And everything started here by means of determination of the vertical asymptote, horizontal asymptote, and how your function behaves when x is 0. Maybe the origin is involved, or maybe some y-intercept is involved. Then come up with two arbitrary points on either side of your vertical asymptote, and you are able to graph it. So this question has been done for you. Now let's look at question number B. Question number B will assume this form. You have a polynomial in the numerator and a polynomial in the denominator. So let's come up with something. 3 minus x over 2x plus 3. We have exponents of 1 here. Start here with your vertical asymptote. Always look at the denominator. The 0 of your denominator, equal it to 0. 2x is equal to minus 3, x is equal to minus 3 over 2. That here is your vertical asymptote. When you have some sort of exponents which are the same here in the numerator and denominator, the horizontal asymptote is slightly more tricky. What you do is you take the numerator expression, you divide it by the highest degree of variable exponent. The highest degree of variable exponent here is x to the 1, which is the same as x. I'm dividing that by x. You do exactly the same with your denominator expression, 2x plus 3 divided by x. Open this up. You have 3 over x minus x over x divided by 2x over x plus 3 over x. Simplify this out. You have 3 over x minus 1 divided by 2 plus 3 over x. Now apply a certain limit as x were to approach infinity. What would happen to areas of x? 3 divided by infinity, it would zero out. 3 divided by infinity here would zero out. Obviously you're left here with minus 1 over 2. This here is your horizontal asymptote. By means of this limit determination as x approaches infinity, after you do this simplification or manipulation procedure. So we've determined our horizontal asymptote is y equals minus 1 over 2. Remember, vertical asymptotes are always x equals, horizontal asymptotes are always y equals. Equations y equals minus 1 over 2. Now graph these out. X is equal to minus 3 over 2 right over here. Y equals minus 1 over 2 right over here. Is the origin or some y-intercept involved? Well, determine f of 0, which means you're looking at 0 comma something. Put 0 in places of x. You have 3 divided by 3. You have 0 comma 1. It tells you 0 comma 1 is involved. You're very much seeing that there'll be a curve here, then there'll be a curve here, but we have to confirm that. Take a value here to the right or to the left of your vertical asymptote. My vertical asymptote is minus 3 over 2. Why don't I just come up with an arbitrary point 2, and on this side I can come up with like a minus 10. When I put 2 here into the places of x, I'm getting 3 minus 2, which is a 1, over 2 times 2 is a 4 plus 3, 1 over 7. What will happen is, based on this points that you can come up with more and more points, you'll have a curve which will go like this, and it will eventually go along the horizontal asymptote right here. Y equals minus 1 over 2. What happens when we put minus 10 over here in places of x? We have a 3 minus minus 10, which is a 13, and then we have a 2 times minus 10, which is a minus 20, plus 3 is a minus 17. I'm getting a negative value, not a very large negative value, but we'll see our function will behave in this way. We'll have here 13 over minus 17. And now you can see our graph has been done. On this side and on this side, bounded and confined by means of these asymptotes. So this video comes here to an end, but remember, start with vertical asymptote determination, then horizontal asymptote determination. See if in some way how the zero placement of the x, how your function behaves. Come up with 2 arbitrary points to help you actually map out your curve, and that's about all there is to it. Thank you for watching.